Now that the drum roll is complete, welcome back to Computer Science E1. My name is David Malin. This is Lecture 5, our second lecture on the Internet. Allow me to introduce tonight by way of the film above you.
He came with a message, with a protocol all his own. Uncaring routers, a dangerous far worse than death. He's fast, he's strong, he's TCP/IP, and he's got your address. Warriors of the Net.
So that is a teaser for a short film we will watch toward the end of tonight's lecture. But before we dive into what TCP and all of that is all about, we are at the point in the semester where it's time to raffle off this iPod t-shirt. Recall that for problem set 1, among the students who submitted, if you received higher than a 75%, you are automatically entered in a raffle. The first prize that we'll be raffling off tonight to students both local and distant alike is this t-shirt, for the first time revealed to the class. This is apparently signifying laptop plus iPod. Okay, and on the back we have a little advertisement, it seems. College students, buy a Mac and get a free iPod. So apparently, I'm not sure under what circumstances you get this t-shirt though, but it came to us nonetheless, donated by Apple. With that said, I'll do a moment of suspense here. And the winner of this t-shirt this semester is Mr. Gerald Walden. Is Gerald here tonight? Gerald, come on down. A round of applause, of course, please. It is entirely your prerogative if you wish to wear this t-shirt, but congratulations. And well done on problem set 1. So, lest you think there's some funny business going on, know that Dan Armendariz served as witness to the one-line program that I wrote before lecture tonight that generated a random number between 1 and 40 that allowed us to select from among those 40 submissions which of you were the lucky winners. I'm going to hold you in a bit more suspense with regard to the iPod Shuffle itself, but let's turn our attention now to, again, this topic of the Internet. And frankly, Google Earth is just too cool not to revisit in this class. So tonight will be entirely about Google Earth, if only because it's the coolest thing that I've wasted several hours on over the past couple of weeks. How many of you, out of curiosity, downloaded this program after last week? So a few of you. So you will be tasked in problem set 4, if you haven't noticed already, with the downloading of this program in order to satisfy 2 of the problem's demands. One of which is to seek out some fairly popular tourist attractions somewhere in the world without us giving you so much as directions or longitude and latitude or addresses. And then the second part of the problem set will ask that you seek out 3 places of interest to you personally. This is more, though, realize than just a fun thing to play with. Know that, 1, the software is entirely free, which means we have the luxury of being able to play with it with the expectation that others in the class and beyond are certainly welcome to do the same. But this is actually, as we explained in the problem set, a wonderful opportunity, truth be told, to appreciate, if you don't typically do so, that you don't need training to use new software. At least you shouldn't need training. You shouldn't need a user's manual to use new software. You don't need to have certifications to use good new software, at least in the ideal sense. And as we try to assure you in the problem set statement itself, if you struggle for the first time you sit down in front of Microsoft PowerPoint or Microsoft Excel or whatever new application you're required to use at your company, to be honest, it's probably more the fault of the application and of its design and of its development, frankly, than of you, the users. And a number of you enter this course with a bit of apprehension as to what you can do with a computer, and dare say you feel you might need training on certain programs and software. Well, the goal of this problem set, in part, besides just having fun taking a little vacation in your homes, is to introduce you to a program that is fairly well designed, I think is fairly intuitive. I'll give you a cursory tour of some of the features, but to be honest, the second sort of implicit goal of this problem set is just to give you an opportunity within the span of a few minutes to download a program and then go figure it out. And that alone can be a sort of empowering trick. But with that said, we've got this spinning globe here. I thought I would take us right away, as we may have done last time, to 1 Oxford Street in Cambridge, Mass. 02138. Just a quick tutorial. And this is the extent to which you will be trained on this software for this problem set. And that's precisely our intention, to give you very little training. At the top left of this program, if you've not used it before, is a little search box. You can type an address in there. Google is pretty good about knowing if you type Eiffel Tower, where in the world that is. So it's pretty good about guessing where certain popular locations are. But you can more precisely specify a US address, a foreign address for most countries, a latitude and longitude, and sort of other tricks as well. I'm going to go ahead and click Enter after typing that in. And if nothing else, to be honest, it's perhaps the fundamentally unnecessary, dare say gratuitous animations that make this program so cool. As we zoom in here to our location, 1 Oxford Street, of course, is where? Right here. So we have now a bird's eye view from a bird that's currently flying at about 3,000 feet. You can see in the bottom right corner of the screen your altitude, at least in feet. You can change that to meters or kilometers if you prefer via one of the menu options. But notice, and it's a little hard to see if you don't know to look for it, certainly on our screen here, in the top right of the screen where my cursor is, there's a whole bunch of controls. One, there is a plus and minus in a vertical scroller. So if you simply click on that plus, as you might expect, things zoom in. If you instead click minus, you're going to zoom out. And then there's also a slider there with which you can sort of move it back and forth without just clicking. But it should be fairly intuitive if you click on the thing yourself. Meanwhile, you can certainly move horizontally and vertically and left to right and so forth to get a different vantage point. Just like Google Maps, if you're familiar, you can click on the display and just drag it around, which is perhaps even more intuitive. And if you're really adventurous and zoom in, for instance, a little bit, and you kind of wonder what this building looks like from a different angle, you can use this slider up top to change your tilt. And you'll get a different perspective on the world. Notice, though, a curious thing happens the more and more we go down. It turns out the Earth is indeed flat. But this is obviously why. This result. Why are we seeing that? Right, so you don't have a satellite looking in your window, you have it looking on top of your house from up above. But there are certain parts of the world where you do have multiple angles, or you have software, the software is designed to sort of interpolate even better what the shapes of those mountains are, or what the canyons are. And we'll go to one such place in just a moment. And this, meanwhile, I'm going to tilt us back up to a more reasonable level. Then you have this big wheel, which by default points you north. But if you click on the big wheel and spin yourself around, you can sort of do a nice 180 spin in that way as well. Meanwhile, do take note, if you haven't seen it already, in the bottom left of your screen, you have a whole bunch of layers. This is a fun place to play around because it offers different features of this program. Notice that I have checked terrain. That's a good one to leave on because for those areas of the world where Google has sort of height information, it will show you more of a 3D perspective rather than an interpolated flat perspective. There's a whole bunch of other options here that you can play around with. If you want to find the nearest pizza place in some areas, you can click on such things as dining or the nearest hotel, and it operates in that regard like Google Maps. But our purpose tonight is to sort of wow. And so notice in the middle left of this screen, under the thing called Places, this is where you can store places you like. And essentially what problem set 4 asks you to do is to, quote unquote, place mark a number of specified locations. This is like bookmarking, but a physical location. And it's terribly simple. There's a little thumbtack here at the top of the program. You click that thumbtack. And notice you get one of these place marks in the middle of the screen. You can then click and drag it around. For instance, I'm putting it on top of Memorial Hall, which is just across the way outside this building. And then up here, you can type a name for it. So I could type Memorial Hall. It tells you already what the latitude and longitude is, if that's at all of interest. And then you can type a little description here, like where freshmen eat meals. For instance, the Annenberg Hall is inside of Memorial Hall. And then you click OK. And that's as though you've placed a bookmark of sorts into this actual world. What we're going to ask you to do for problem set 4 is to submit via the website's Dropboxes those place marks. And the means by which you do this is very simple. Notice that this place mark ended up under this My Places section of the page. Moreover, as the problem set does tell you to do, notice that if you, for instance, right-click on this with a PC or hold and click, say on a Mac, notice that you can say something like add folder. And what we ask you to do in the problem set is to create a folder called 3, I think, and another folder called 4, respective to problems 3 and 4 for the problem set. So I'm just going to type 3 to create the name. Notice I get this 3 folder, and as you might hope, you can simply click and drag Memorial Hall to your 3 folder. And as with other interfaces, notice the pluses and minuses that appear. That'll expand the thing or collapse the thing. And finally, what you'll do for problem set 4 is when you're all done and you've found all the locations in the world that we've asked you to find, you'll simply, for instance, on a PC, right-click or hold and click on a Mac, and then you're going to go ahead and say Save As. And then notice you get a familiar dialog window. You can go to your desktop, and you can say My Place Marks, or rather we'll call it 3 in this case. Notice the default file name is going to be .kmz. It's a little small, but you'll see as much on your own machine. And then just save it. What that just did was put on my desktop a file called 3.kmz, and that's one of the files you will upload for submission. And what that's going to let the teaching fellows and me do is open your place marks, click on those hyperlinks, and whisk ourselves away, not only to the places you found, but also the places of personal interest that you drew our attention to. Questions at all? I mean, to be honest, if that is not sufficient direction, and frankly, you have the video as the reminder, it's not meant to be an exercise in remembering what David said, how this program works. It's meant to be exploratory. If you don't know how to do something, poke around. You're not going to break the software, certainly. But it's only so much fun, if at all, listening to me talk. Why don't we take ourselves on a very brief tour, perhaps to one of these places where terrain is of interest. So notice that Google gives you by default this sightseeing folder. We created an empty folder a moment ago, but the program comes with a folder called sightseeing with a whole bunch of popular locations. And why don't we whisk ourselves over to the Grand Canyon? It suffices just to double click on that thing. Notice we're heading out west in this country. We're about to zoom in. And the Grand Canyon is a wonderful example of if you have the terrain layer on, you'll actually get this 3D mapping. And then if you really want to have a sort of IMAX experience, you can use the keyboard to navigate these controls besides just using the top right. And you can sort of fly your way through the Grand Canyon and give yourself a little tour. It's really wild. And notice, by contrast, if I turn off terrain, there you go. That's the Grand Canyon. So it does make a difference. Finally, let me offer you one other demo of my own design. Let's whisk ourselves away to Boston, Massachusetts. And again, little tricks like Boston, MA. That's sufficient. Google's smart about figuring out what you mean. We're going to jump over here back to Massachusetts. It's going to zoom in. Here we have the main part of downtown. If I drag it over, you can see Boston Common there, the big green area in the middle. But let's focus in on the financial area, or right downtown, and click on one of these other layers, namely 3D buildings, in just a moment. First, I'm going to zoom in, and you can see that these are pretty good photos of these buildings. But if you want to really get a 3D perspective, some cities have support for 3D buildings. People have built virtual models of these buildings such that now, if we dive into the middle of Boston, and sort of change our perspective, you can actually see what the city looks like from a 3D perspective. And you can do this for some of the major cities. New York is another one, and so forth. Now, here's where you get to partake. Before we go back to understanding the internet, let's use it for just one more minute or so. Where in the world would you like me to take you on this tour? London. So London, UK. Whisk ourselves away over the Atlantic. And in just a moment, we will find ourselves in central London. So there's the Thames, looking a little murky as always. And if we scroll ourselves here, it looks like this is the London Eye that it's taken us to, right there. So the big Ferris wheel of sorts in London. Oh, one other thing, especially for those of you who use public transportation. Let me take us back real quick to Boston, Mass. Show you one other layer that's kind of fun. I'm going to turn off 3D buildings by unchecking it. And then I'm going to turn on, under transportation, I'm going to turn on transit. And if you've ever wondered topologically what the MBTA system looks like, you can see it now with this nice overlay, not only for the subway, but also for the commuter rails if you zoom out. And the coolest thing, frankly, I never get tired of this, if you just hold on the keyboard and zoom out, I mean, it's like you're making your own movie, right? 2001 style. So, in any case, one more place. Where do you want me to take you?
Big Bend National Park.
Okay. Sorry? What?
Big Bend National Park.
Big Bend National Park. Oh, Bend, okay. Big Bend National Park. Let's see. Here we go. Good. Another one where terrain is nicely depicted. Here, too, I'll tilt this back on an axis, and you can really see the 3D there. So it's pretty wild. So, in any case, have fun. We're giving you, 20 or so points to sit at home having fun, maybe showing off to your family or friends exactly what your homework is on that part of the problem set. There is more to the problem set, and realize that this problem set is intentionally not due until the 8th of November, which may seem like a long ways off, but that's because this problem set in particular is fairly involved. And not in a difficult way, but in a fun, as we say, way. Among the other challenges of the problem set is actually to have you go to a local computer store and take your newfound vocabulary, jargon, and comfort, presumably, with hardware and software and the internet to a local computer store and buy, quote unquote, with some virtual dollars of ours, up to 2,000 virtual dollars, some computer equipment. And this process is all about empowering you with a bit more comfort in, one, reading the tags on the shelves, two, giving you finally that sense, if you've never experienced it before, that you do in fact now know more than the salesman or saleswoman who's trying to sell you that computer. And two, or three, as we qualify in the problem set, we do suggest, since we do this every year and we therefore alienate all local computer stores about once a year, that you not advise the staff until you're done with your assignment that your dollars are in fact virtual. You won't get nearly as much assistance. With that said, any questions about problem set 4, before it, or anything beyond this point in the course? All right, so enough about Google. So I connected to my mom's computer remotely in Connecticut last night, installed this on her computer, Google Earth, and that killed the rest of her evening as well, taking a look at all of her favorite places. So it's addictive, so beware. All right, so the internet. So last week, and certainly part of tonight, we focused more on the things you can do with the internet, the types of services that it offers. And let's take one step back to last week and pose the following question, since it's sort of one that recurs every year. Are the internet and the World Wide Web the same thing? All right, so no. Let's qualify that now. Why? What's the distinction between these two? Yeah. So the internet is an operating system within the World Wide Web. I tweak that slightly. And before I tweak, let me see if there's another suggestion. Yeah? Let's go with this one, because it's a bit more precise. So the internet is a network of networks. It's an infrastructure. And I would beware using a term like operating system only because that's too easily conflated with desktop operating systems. But it's an infrastructure. It's a framework. It's the backbone on which applications and services run. So when we talk about the World Wide Web, we're effectively talking about something you can do on the internet. And this use of preposition it's not coincidence. It's the fact that you really are using a service on top of the internet. Whereas the internet itself, though you can't necessarily point to it and say that's the internet, because it really is this network of networks of networks, well, it's more of the physical infrastructure underlying all of those services you run. So what tonight is about ultimately is about lifting up the hood of the internet, looking at how it works. When it breaks, what does that mean? When your own computer doesn't connect to the internet properly, what does that mean? When you call up Comcast or Verizon and are trying to diagnose why your internet connection is down, well, what kinds of questions can you yourself ask or answer for them? How, in short, might you go about picking up that phone and rattling off so many technical words in the right order and with the right usage, that the person on the other end is convinced that you don't need to spend the next hour on the phone with them. You can get bumped right up to, say, level 2 or level 3 tech support. It's a wonderful skill. If you can rattle off more information than the person on the other line understands, usually, though not always, sadly, they'll realize that it's much easier for them just to pass things up to someone else. And frankly, certainly early on, you can probably get away with using all these words and not necessarily in the right order, but enough of them that you get your way past the initial tech support call anyway. So let's, as always, start from sort of the bottom up and then build up to the juicier, more interesting things. You've got a couple of computers. Say you've got 3 computers. How could you go about, topologically, connecting these things together? Well, what does this mean? Well, last week we talked about the smallest possible network that's at least interesting. And that had 2 computers. And we drew our very dated picture of a computer like this. And we said connect it via some wire or some connection of some sort. And there you have what kind of network? Peer-to-peer network. And again, to be sure, that term has taken on a broader meaning these days in terms of the Napster-like softwares of the world and so forth. But peer-to-peer can also mean quite literally that. 2 peers, 2 equal computers, effectively, communicating back and forth. And this was just to make a distinction between a similar pairing, but a relationship in which I intentionally drew one computer bigger. And when we drew one small computer connected to one big computer via some connection, we described that relationship in terms of 2 other buzzwords. Client-server. And none of that was meant to say that servers are always bigger than clients, but it's just meant to suggest that just as a restaurant can handle multiple clients, multiple customers at once, so can a server handle multiple requests. For instance, it's a web server from multiple clients at once. Well, now enter in computer number 3. Well, it would seem, just intuitively, that if we've already got those 2 computers connected together, how in the world can we introduce a third? Right? We could disconnect the middle guy and plug the left guy into the right guy, but now we still have a peer-to-peer network of 2 computers. OK, so using a server, I heard. What was in back? OK, so turn one into a server. What else might we do? What else might we do? Sorry? Yeah, so let's go there, because this is probably a device that you're all perhaps owners of if you have multiple computers connected to your internet connection. Well, rather than trying to connect them all together, we could certainly connect them to one central computer, as was suggested, a server. And that server can sort of figure out how information might go from, and this might be our server here, how information might go from A to the server, then the server could send it to B, or the server could send it to C. Well, it turns out that's a very reasonable solution, but it also turns out that this notion of routing data among computers from A to B, B to C, C to A, it doesn't even require a computer or a server in the conventional sense. This problem can be implemented in very small pieces of hardware. So yes, you could view these pieces of hardware, routers as they tend to be called, as computers, and they are, but they're not computers in the monitor, keyboard, mouse sense, at least. So one way that we might connect all these computers together then is not so much directly from one to the other, and we don't need a whole other desktop and monitor to connect these 3 guys to. All we need is some central point. Connect this computer here, this computer here, this computer here. This solves the problem of these computers presumably only having one port on the back into which you can plug a network cable. Recall in our first or second lecture when we looked briefly at some of the ports on the back of a computer, and maybe in section you did this as well. Well, they take these telephone jack-like plugs. They're a little fatter than a typical telephone jack. Well, a typical computer these days only has one of these jacks. Well, if you only have one of them, you've got to put the other end of the cable into something, and it clearly doesn't work to just connect 2 together, because then the buck stops here. You can't go any further. So you connect them to a central device like this that clearly must have multiple Ethernet jacks, as they're called. So the technology via which many computers, dare say most computers today, at least so far as we are concerned, the technology that they tend to use is something called Ethernet. So if you ever hear someone talking about an Ethernet cable or an Ethernet jack, for all intents and purposes, they are talking about this standard telephone-like cord and the jack that it plugs into. And the jack specifically, just to throw out something you can impress others with, is called an RJ45 connector. And this is in contrast with a telephone, random trivia, that's called an RJ11 connector. Just think of it doesn't necessarily grow out of this, but 45 is bigger than 11, so 45 is the fatter cord. Might be a simple way of remembering that. Frankly, if you never remember that, you won't be terribly worse off than you are right now. But seeing it in print is useful if, for instance, you go to the store and you want to buy a cable so that you can connect your computer to one of these central devices. Well, what do you get? Well, you ask for an Ethernet cable, a network cable, a cable with RJ45 connectors on the other end. You might see things labeled differently depending on the circumstances. But let's slap a label now on this thing. We called it a router, but it turns out you don't really need a router per se to have data transmitted among 3 different computers. Call them A, B, and C. This device can simply be something known as a switch. So a switch is quite simply a relatively cheap these days and relatively dumb device whose sole purpose in life, upon receiving data, that is bits, from computer A, looks at those bits and realizes, oh, you know what? These bits are intended for computer B, and so it sends it from this jack, this RJ45 jack, out this jack. If instead it receives some bits from A, and somewhere embedded in those bits is the label C, well, a switch is designed to send those bits instead to computer C. And switches they're not completely dumb. They don't just spit out all the information that comes into them. Rather, they do intelligently select, almost always, which jack out of which it should send the received data. So the reason we qualify switches as being distinct from routers is that those little blue and black devices you buy, or those silver devices that you call home routers or call firewalls, they are so many things in one these days. If you have one of these devices that gives you the ability to run multiple computers off of one internet connection, you would be correct most likely in calling that a switch, a router, an access point, a firewall, a proxy server, and dare say a whole bunch of other things as well. That's just because at the end of the day, it is a computer. It has no monitor, it has no direct keyboard or mouse, but it is a little computer that has embedded in it software that does all of those things. And it has the hardware, that is the jacks, that physically allow those kinds of features to happen. And tonight we'll tease apart what some of those features are. For instance, what a router is, what a switch is. But for now, it suffices to realize that, well, you know what? We can, in fact, connect multiple computers together with a device like this. How much is it going to run you? If you've got a few computers at home, you want to connect them all together, well, how much are you going to pay for this kind of switch? And all a switch is, and you can see this perhaps in section, or you can see it in your own homes, it's got a power adapter that you plug into the wall, and it's a little plastic or metal box that has a whole bunch of these RJ45 jacks. That's pretty much it. No moving parts or switches. No pun intended. How much? 20 bucks, right? Almost always in this class, frankly, these days, everything 20 bucks, 10 bucks, 30 bucks. Relatively cheaply these days. And if you watch for rebates and you're really careful with your money, you can sometimes even get these things for free after rebates, maybe plus shipping. So what topology are computers usually connected in these days? This sort of mishmash here is meant to beg the question, when you have multiple computers, how do you connect them together? Well, what you've seen an example of is what's known as I'm going to skip ahead, a star topology. This is probably the most common way of connecting multiple computers together in a network these days. You wire all of them to some central point. In fact, if you are really a geek or live with a geek who has him or herself multiple computers, or you work in an office where you have a server room, or you have jacks into which all of your coworkers' computers plug in, well, ask your IT guy sometime this week, where is your server room, or where is your wiring closet, or where do all these wires go? And if the place is laid out nicely, there probably is somewhere in your office or building some kind of closet or room that you can walk into, see a whole bunch of wires coming out of the wall or coming through the ceiling or from the floor, and all of them get plugged into all of these little jacks on a rack. So computers and server rooms are usually laid out in big metal racks, and what you see is switches that don't just have 3 jacks, but rather might have 24 or 48 or 100, so that you can plug a whole bunch of computers into. Well, many of you probably have those internet jacks on your walls. Let's see if there's one in the room. Most everything's wireless these days. So back in the day, there would have been on the wall somewhere one of these jacks into which you at work plug your computer. Well, all that is a cheap little box that has a jack. Behind that jack is one of these wires. That wire most likely leads to that closet or room in your building or company. And on the other end is another one of these RJ45 jacks, and it plugs into a really big switch. And by big, I just mean physically, so that you can fit a lot of these things, so that all of the computers are through that switch interconnected. And so if you have a file server at work or printers shared at work, it all boils down to them being connected, usually these days via Ethernet, via cables and switches like these. In yesteryear, and the reason for the other pictures is you could connect computers in other topologies, which we won't dwell on since it's simply not as common these days, but you could go the ring approach, which several years ago was common, if only because, one, that's what some of the original protocols, languages that computers spoke when networked were designed to do, and two, it's also cheaper. When cabling was more expensive, you don't want to necessarily run wires from every computer in your office all the way to the basement or all the way to the attic. Because think about the waste. Much more sensible, it would seem, would be to run those wires to the next closest computer and from there to the next closest and save on costs. These days, you pay pennies for this kind of cable. In fact, 2 or 3 years ago, the teaching fellows and I bought a box, a spindle of this kind of cable. The cable itself is called usually Cat5, Category 5. It just means it's capable of internet speeds today. We spent $50, maybe $80, and I thought every year we'd have to get a new box because in section we use this cable. We're still working off of the same box for 3 years now, which means we pay pennies per foot of this thing. And you may wonder why this teaching staff and I need 1,000 feet of this cable. Well, one of the things you'll do in an upcoming section if you're local is actually make your own Ethernet cable. Now that seems a bit weird if I motivated some of this discussion earlier with how to go buy such a cable from the store, but there's a remarkable, I think, sense again of empowerment and also frustration when you try to take the 8 little wires that are inside one of these cables, line them up in just the right way so that you can slip on one of these half-cent RJ45 connectors. You slip those wires in. You take a little crimping tool that we'll hand to you. Squeeze it as hard as you can. Usually pass it then to the TF who will squeeze it even harder for you. And then at the end of the section, if all goes well, we will test out your cables on a working computer. And if we can bring up a web page, you've done good. And if we didn't, well, you will walk home with your head held low, perhaps. But it will be, for those of you who get them working, a wonderful souvenir to take home to friend or family. And in fact, let me take this moment, as we tend to do. You know, in this class, despite how we try to teach you how to make computers and upgrade computers, we always seem to go through more computers and equipment than we actually retain. So I'm going to take a knife to one end of this otherwise working Ethernet cable. And I'm going to cut off part of the plastic sheath, because even though this thing looks pretty thick, all this yellow thing is just a piece of plastic or rubber that keeps all of the little wires in there sort of tucked together and secure. So I'll pass this around now, and any of you who have an internet connection at home that uses a cable modem or DSL modem, you have one of these in your home. And if you have a wired connection at work, you have one of these in your home. So take a look as this comes around at the 8 wires that are now coming out of this thing. And again, in section, your goal will be to line them up in the right way and crimp them back down. But then notice, too, on the other end of this thing, that those very same colors and those very same wires are lined up in a certain pattern. And therein lies the challenge. You can't just plug 8 wires in on one end in any old order, plug the other 8 in any old order, and expect them to work. They all have to be lined up so that what comes out this end goes in that end, and so forth. So I'll pass this around, and also one of these RJ45 connectors. So that, sure, I'll pass these around so that you can see exactly what's going on inside these cables. This is not to say, to be clear, that you should ever have a burning desire to crimp your own Ethernet cable. Every time I do it in my apartment to run some new line, when I got a TiVo, when I got a Sling box, and when I just got too much free time, I end up banging my head against the wall. And I sort of wonder, why do we make the students do this? But in the end, it is in fact possible to do this. Another way that you can lay out a network is via a bus network. This too is somewhat dated, at least for today's purposes, whereby you essentially run one wire or line in between all the computers and then connect each of your computers to it, sort of like bus stops or driveways on a local street. So network topologies. All right, so we know then how to connect computers locally. It takes a switch, it takes some Ethernet cables, and it takes the computers themselves. Thinking back to last week, if I draw a very poorly formed building with a door around these computers, well, just to put this into context, what did we call that kind of network? Local to, say, one building. Yeah, so that was our LAN. So even though we're focusing more on the details underneath the hood tonight, it's really the same tale as last week. But once you have a LAN or a bunch of WANs and you actually want to connect these things together, well, how do you go about connecting them together? Well, therein lies the design of the internet. So we said last week that the design of the internet grew out of a US military project called ARPANET, one of whose design goals was to have a fairly well distributed and redundant network so that there was never just one path, ideally, from A to B. You could go from A to C to B, from A to D to B, and so forth. But in short, there was never just one wire connecting two important sites. Well, what you have these days in the more popular usage of the internet are what are just generally known as internet backbones. So companies like MCI and AT&T and the big fish, so to speak, with which you're familiar largely from the telco days, in fact, own a lot of the underlying infrastructure that the internet ultimately is defined by. And by infrastructure, I mean really fast, really thick wires, thicker at least than these things with just 8 wires, that carry not just a local network's traffic, but can carry gigabytes of traffic, terabytes of traffic, theoretically. You have lines not only in the US, certainly, but you have transatlantic and transpacific cables, hundreds of feet below water, that themselves are carrying a whole bunch of cables that in spirit work similarly sometimes to these kinds of cables, which are copper wires, and you can do much better with the right kind of money and right kinds of technology. Some of these cables these days are fiber optic. One of the other cables I'll pass around is this orange cable. Notice as this thing goes around, those are just copper wires. If you pull off the plastic colored sheets that are around the 8 individual wires, you'll just see some, bronze or copper colored wire. And it's just sort of in a flow of electrons across that wire. Contrast that with something like a fiber optic cable, which this is more expensive, and we're not going to clip the ends off of this one tonight. But how does data travel along a fiber optic cable? It's fundamentally different from a copper-based cable like that. Yeah, it's effectively traveling by way of light. So not so much the flow of electrons across a metal wire, but rather flashes of light, if you will, across a medium that is conductive and allows the passage of light, not just in a straight direction, but through a cable, in effect. And you all might remember, say, from grade school, that even if you don't remember that light travels at, 3 times 10 to the 8th meters per second? Well, you probably remember that light travels really fast, whereas anything that tends to be based in electricity, or at least that flows on something that has resistance, like a metal wire, tends to be slower. So fiber optic cables tend to be even faster. And folks building homes these days, or renovating homes that are building into them network capabilities so that they have jacks in the various rooms of their homes, will sometimes lay not only Cat5 cable these days, but also something like fiber optic cable. Not so much because it's necessary or useful yet, but you see how fast things move these days. It probably is useful and cheaper than pulling, breaking through the walls 10 years from now. And just to put some more numbers and just jargon, all of which you see perhaps anytime you read something tech related, Cat5 cable is essentially capable of operating at up to 100 megabits per second. 100 megabits per second. Contrast that with fiber optic cables, which again can go into the gigabit range. And you can also have cables that are in the 1,000 megabits, or rather 1 gigabit range themselves. But in short, if you're using the kind of wire the yellow wire that we're passing around there, you can have flow about 100 million bits per second. And that's pretty good. In fact, think back. Actually, did we We'll come back to that in just a moment, exactly where the bottleneck might be in your own home. Yeah?
How much does the fiber optic cable cost per square foot, and how soon will it be useful?
Good question. I will punt on the first question since I'm not sure offhand, but a quick Google search could probably turn up the cost for us per square foot of fiber optic cable. How soon will it be useful? It's already useful. Much of Harvard Yard, for instance, is already wired with fiber optic cable because even though the dorms and the buildings themselves are only wired with, say, 100 megabit wire, Cat5 cable, well, once you start connecting buildings together, that suggests that you're connecting maybe a few dozen or a few hundred people in one building to the few hundred people in the other building, which suggests you need more bandwidth. That is, more ability to have bits flow between them. So you see fiber optic cable being used certainly in larger networks. But in the home?
Like a residential condo. Like if I'm renovating a bunch of condos, is it worthwhile if they're not, if it's not a huge size?
It's a good question. So if you're renovating a residential condo, is it worth wiring with fiber optic cable? I'll go out on a limb and say it's probably slightly premature. Consider, after all, a point we'll get to tonight, which is that even though Cat5 is capable of 100 megabits per second, we can jump ahead here because it's an interesting question. How fast is your typical internet modem, cable modem or DSL modem?
30.
Sorry?
Maybe
30. 30 what? 30 megabits per second, maybe, although if it is, I'm quite jealous because that's somewhat high. A cable modem typically these days, another thought or another proposal? So a cable modem tends to be, I would say, between maybe 1.5 megabits per second to Comcast, I think, currently offers up to 8 megabits per second. A DSL modem, meanwhile, offers a speed of what? 20 megabytes. Wow, you guys all are getting much better service than I am. So usually not. I'll say not with DSL, at least. I would say typically you see slower speeds with DSL, although you're seeing a convergence these days as Verizon, for instance, in Boston and Comcast become more competitive. I'll say that generally, and again, these numbers are just typical. They're not necessarily upper and lower bounds. You might get something like 768 kilobits per second to a few megabits per second. These days, though, Verizon in Boston, if you pay for DSL modem service, which for our purposes is different only insofar as DSL modems come in over your phone lines, cable modems use your coaxial cable lines. Beyond that, that's the physical difference. The real world difference is that these days, at least in the Boston area, cable modems tend to be faster. And in fact, if you go and, but what's the flip side? You can sort of spoil the answer. What's the upside of DSL in the Boston area and elsewhere, certainly? Well, Comcast is better in that it tends to be faster. Right? It tends to be more expensive. Right? We saw that same trade-off talking about RAM and hard disk space and so forth. So for instance, Comcast, frankly, it's a little insane. I think you pay between $40 and $60 a month for Comcast service, depending on if you have cable bundled with it and phone and all that, but it's pretty high. Whereas DSL, even though you can get introductory rates for like $14.95 or $19.95, I think their current rate is probably 25-ish, 35 max. So I'm going to say, I'll say something like 15 to 35, but take these with a grain of salt, but it does tend to be less. But, and for the uninformed, this isn't such a problem. It's very hard, if not impossible, on, say, Verizon's website to find out what the speed is of their cable modem service, of their DSL modem service. What they will typically do these days, which is a bit misleading, is say that it's 40 times faster than dial-up. Well, who cares? Like, how much slower is it than cable modem service? Well, notice, too, that these numbers are somewhat misleading because, in fact, even though I get, for instance, at home 8 megabits per second download, usually, or a lot of the time, your upload speed is much slower. And it's an asymmetric medium, whereby, yeah, you'll get up to maybe 8 megabits per megabits per second, lowercase b, bits, megabits per second. What is my maximum upload speed? Of course, only I know this, but take a guess. Much slower. Good, we'll take that, an E1 answer. Let's push a little harder. 1 to 3, yeah, it's actually even sadder than that. 768 kilobits per second. This, mind you, is because I pay $10 more a month to double my upload speed. It's a funny thing. So with Comcast, again, you'll pay 40 to 60 bucks a month, and the typical speed they quote you, at least in the Metro Boston area, is up to 6 megabits per second and up to 364 kilobits per second upload. That's okay, though. Why does it tend to be okay for the typical user to have this asymmetry, whereby downloads are much faster than uploads are? Right, I mean, you tend, as a typical user, to download far more than you actually upload, right? What are you doing when you're on the internet? You're pulling down web pages. You're sending very little requests. You're saying, give me today's news, and then all of CNN's news gets sent back to your computer. If you're downloading MP3s, you're sending a very small request, give me the latest MP3, but then you're downloading 3 megabytes of that file. If you're downloading movies, you're downloading hundreds of megabytes of files. But how often do you, say the typical E1 student, upload a movie that's 200 megabytes somewhere else? So the sort of and this is where you start to see the distinction between people like us down here and people like you. What we do every day or often is the other direction, sending data up for research purposes, for course purposes. Every time, frankly, we upload the latest videos to the podcast, it's the biggest headache because it saps my internet connection for an hour or two, usually every Wednesday night. But fortunately, Lost is on Wednesday nights, so it's not such a problem. But the point is that you have this asymmetry, and you got to read the fine print sometimes to know the difference. And you also have to understand what your needs are so as to know, does this matter to me? DSL will similarly have this asymmetry, and it will sometimes be quoted. But again, you have to beware. Verizon in particular has kind of dumbed things down enough in a marketing sense, where again, they say 40 times faster than dial-up service. But even if you get a salesperson on the phone, they'll tell you, well, it takes no more than 53 seconds to download a movie. Well, what does that mean? Like, how big is the movie, and what are we comparing things to? So you have to bear that in mind. But typically, if you want really fast speeds, cable modems tend to be better. But again, even here, there's a caveat. I pay, again, 10 bucks more a month to double my upload speed from 364, which is normal for Comcast, up to 768. And for me, that's huge. It literally halves the amount of time it takes to upload one of E1's podcast videos. Or if you recall from our first lecture, Slingbox, when I think we were showing Press Your Luck on the overhead screen, or some TV show, Slingbox being the device that streams my cable TV connection this way. You know, I'll admit, I like to tell myself that I pay 10 bucks more a month so that I can work more productively. But frankly, it also has the fringe benefit of doubling the quality of watching TV remotely. But you pay 10 bucks more a month, and you go from 6 megabits per second download to 8 megabits. Now, that sounds like a lot more, right? That's 33% more for only $10. But you have to ask yourselves what question at that point? Well, do you need it? So yes, it's faster. But your internet connection is not the only bottleneck in the world. The person you're downloading that file from might not have as good an internet connection, especially if it is one of these peer-to-peer file sharing programs. If you're downloading even from a big server like iTunes or even E1's podcast, the server is configured to send you the file somewhat slowly. The presumption being, well, we want to be able to satisfy lots of downloads at once, but you don't really need that video right now. You're probably okay with waiting 20 minutes instead of 15 minutes to download that file. So there might be artificial delays on the other end as well. The problem is that I don't need more download speed. 6 megabits is pretty darn fast, at least so far as typical computing needs go today. It's this where they really get you. And it's hard to go beyond this speed unless you want to pay much more for it. However, those of you who are commuting in from Boston or who are watching this show from outside of Boston, from folks like Verizon, have the advantage of an up-and-coming technology known as Phi OS. And if you've got this, then I am genuinely jealous. This is a fiber optic-based technology for delivery of internet connectivity to the home, and it does tend to be much faster than cable modems. And I don't remember values offhand, maybe the TFs know. I want to say something like 10 or 20 megabits per second. in theory. It might be a little pricier, but some of you in the outer areas of Boston can get this already. So I would go to Verizon.com and search around for FiOS, fiber optic, and so forth, and if only out of curiosity for yourselves, if you can get it. So, in answer to your question, is it worth wiring a condo, one's own condo, for instance, for fiber? Honestly, probably not, because even though you already have the ability to wire your home pretty cheaply, pennies per foot with Cat5 cabling or Cat6, which is slightly better insulated, essentially, you look at the incoming internet speed. So you could have a really zippy home network, but where's the bottleneck? It's in the jack in the wall, where your home interfaces with the outside world. So the only advantage really to wiring one's home or apartment with something better than, say, Cat5 100 megabits per second would be for what kinds of situations? What kinds of people would want to wire their home, say, with fiber optic cable? So if you upload a lot, it doesn't matter actually, because this is symmetric. You do get 100 megabits down and up, but you only hit that asymmetry once the data starts to leave your home or your office. Why might you want a really fast connection locally, even though it's not going to speed up your connection to the outside world? Because again, the bottleneck is at the jack in the wall. Yeah, so to share data among your own computers. So companies, certainly, and Harvard, universities, campuses will wire their local networks with faster technology so that, one, you can have peer-to-peer file transfers happen more quickly. Students on campus, for instance, could stream this course's videos at a much higher resolution than outsiders could using the general internet. And two, if you run your own file server or backup server, which even though this might seem a little geeky these days to imagine, I might in fact be one of the few people in the room with a file server in his apartment, well, the more the world talks about having like home media centers where you store all your movies and music in a central computer, essentially, in your entertainment center, well, sharing data even within the home is becoming a much more plausible and compelling feature. So you will see that in the future. But again, I think you'd probably be overpaying at this point. But again, it's conjecture. You can, in fact, save money sometimes by buying, long story short, special cables that have pretty much everything inside of them, sort of planning for a rainy day. Coax cable, Cat5 cable, fiber optic cable. So it just depends on the cost and if you think it's worth it to you. But as to when that day arrives where it's fast enough, it's useful and fast and necessary, tough to say. Okay. Long answer to one question, but we were going there anyway. Other questions? Yeah? Yeah, so municipal wireless. Let's, Chris, how many minutes do we have on tape? 7. OK, so let's go here now before our break and just relate this same conversation to wireless, because it's very much in the same vein. So municipal wireless is sort of something that's being touted in a number of major and minor cities. Let me come back to that in just a moment and say first that for your local network, this is the kind of technology that you're using for a local network if you have, say, the yellow wires that you're running around your apartment. So, or if you're in your office and you're plugging into the data jack, that's probably the kind of wires you have there. But if in your home you have wireless access, or even if your office, or in Harvard, you have wireless access. Notice, and it might be obscured by this big light, but there is a little box on the wall here with 2 little antennae that's plugged in with one of these yellow cables to the wall. But that is allowing all of the TFs, for instance, and some of you to use Harvard's network wirelessly. Well, what is that technology called? And this is not an internet providing technology as much as it is a local area technology. You have technologies like 802.11b and 802.11g. If you have a laptop or even a desktop that has wireless capabilities, odds are you have a piece of hardware in there that supports one of or both of these technologies. The speed of your internet connection locally, if you have 802.11b, is, anyone know? 11. Yeah, it is in fact 11 megabits per second. However, that is signal strength dependent. So ideally, you have 11 megabits per second of throughput within your own apartment. Is that OK? Well, odds are that's plenty. If you were trying to use the internet in your own home, why? 11 seems much smaller than 100. But why is that probably okay and not cause for worry or to feel that you skimped? Yeah, so I mean, look at the incoming connection speed. If this thing's only coming into your home at 8 megabits per second, all you need is 8 megabits per second within the home. And in fact, even though it's maximally 11, it does depend somewhat on signal strength. So if you have lots of cement or very thick walls or brick walls, or you're on a different floor of your home, for instance, you're not going to get as strong a signal. Those of you with Windows laptops will see in the bottom right corner of your screen, if you're using a wireless connection, excellent strength, very good strength. Well, that's sort of a nice way of saying you're getting 11 megabits per second. You're not getting 11 megabits per second, but not all operating systems are precise as to what your actual throughput is. So fortunately, you can do a little bit better, and this is more common these days, G, which gives you what throughput? Oh, sorry? 54 megabits per second. This too is somewhat signal strength dependent, but odds are, even if you're only getting a half quality signal, well, that's still, 27 megabits per second, just speaking off the cuff, and that's more likely to guarantee you this throughput here. And in fact, just to put it into perspective, when I finally did set up this supposed file server in my apartment so that I'd have a central place for all my data and backups, I actually bought a NIC, a network interface card off of eBay that would fit in this specific Sony laptop, but whose technology was G instead of B. Because for sharing files in my apartment, when I load big files from my file server onto my laptop, all right, this is 5 times faster in theory, and that means a big speed up for me locally. So again, you have to consider what are your needs, what are your metrics for actually having a good connection versus a bad connection. So finally, in answer to your question, these Wi-Fi, and this stuff, the cute marketing speak is Wi-Fi, wireless fidelity. You have something called WiMAX, or other variants of this, for municipalities. I just read recently one subset of Boston would be rolling this out sometime in the next year or two, sort of as an experiment. These speeds, did any of the TFs know what they're quoted at? I think it's, I don't want to, let me check during break to come back to you, so I'll hold you in suspense. But it is an interesting question, because one, just to put this into context, you now have free internet service potentially competing with the likes of Verizon and Comcast. Frankly, I don't mind so much that you'll see more of that kind of competition. But it is an interesting question. And I would actually wager that coming from the government, huge expenditures of money in wireless infrastructure, I don't think these things will last, at least in their proposed form, for very long. Because we've all seen, even in this course, right? What we did last week is out of date already. So you can only imagine spending millions or hundreds of thousands of dollars on wireless infrastructure. It's not going to endure for very long, and I question the interest of public service in keeping up the expenses of these kinds of services. I think it's compelling to have wireless service. It's not clear to me if it's going to be sustainable coming to the world for free, at least from local governments. But it's a nice experiment, if nothing else, and it's going to push the envelope in terms of wireless speeds. And frankly, 40 to 60 bucks a month, that's one of my biggest utilities of the month. And I use it every day, but it's only so much I want to pay to watch TV outside my apartment. Let's take a 5-minute break. All right, welcome back. So what do we got done so far? So we talked about how a LAN works, really, underneath the hood. We talked about how you can connect your own LAN or your own local computer to the rest of the world by way of some internet connection via any of these technologies, cable modem, DSL. Ray was kind enough to look up the current speeds for FiOS, and maximally you can get up to 30 megabits per second download and up to 5 megabits per second upload. So not too shabby at all. Again, you can check out Verizon.com to see if it's available to you. Odds are it's not, because it hasn't been rolled out terribly so, but it is being rolled out more in the suburbs than in the local city. So once you've got your connection to the internet, what does it look like? Well, again, this is where we began our discussion. So you have these internet backbones, which essentially are really fast computers and really fast wires that interconnect major points on the internet. And you might hear those points called peering points. A peering point generally or a point of presence, it tends to be areas of the internet where major backbones connect, where Sprint connects to MCI or to AT&T and so forth. And so these very popular nodes here, one in Chicago, Los Angeles, Dallas, and so forth, are major peering points, major points of presence that internet connections, big ones, flow into and flow out of. And some of the interesting things that on this macroscopic scale big companies like the Sprints and MCIs of the world need to think about is the cost of running their own network. And often you will have arrangements between these big providers whereby they pay each other to take traffic from one network onto their own or to put traffic of their own onto another. And one of the curious things about the internet is, one, we already know that data doesn't necessarily have to travel from A to B via one fixed route. Right? That was the fundamental design early on in a network like the internet. But it turns out sometimes the fastest way, the quickest way from point A to point B is not even the proverbial straight line. But rather you'll have data hopping around cities, around within cities for either one, technological reasons, because the data is simply flowing along the fastest possible link, not necessarily the shortest possible link, or because of various peering arrangements and ISP configurations, it's their choice that they want to route your data this way, then back that way, simply because, for instance, it might save the backbone money rather than having to put your data on some other network. For you, the user, none of this is even that relevant, because at the end of the day, presumably, you only care about where your data or that your data is arriving, either at your computer or at its destination. But on a higher scale, there are some really interesting network-related topics that you can actually explore in other courses here and elsewhere if you take a fancy to this kind of topological discussion. But if you've got such complexity manifest in diagrams like this, how in the world does data from my computer even get to CNN server somewhere in the world or Google server somewhere in the world? Well, it turns out that every computer on the internet has an address. Just like you, assuming you receive and send postal mail, have a US Postal Service address in this country that uniquely identifies you or your mailbox or your PO box or your building in the United States, so do computers have an address that uniquely identifies them on the internet. This address, this IP address, Internet Protocol address, is a number that's 32 bits long, which is to say every computer on the internet has an address that's 32 bits long. Thinking way back to lecture 1, how many computers does this naively suggest can be on the internet at one possible time? If each computer must have an IP address, and these IP addresses are themselves 32 bits long. How many possible IP addresses are there? I'll give the E1 answer this time. A lot. But how many? There was one number I begged you to remember in lecture 1. 256 would be unfortunate if you could only have that many IP addresses in the world and on the internet at the same time. It is much more than that. Bigger, yes. So we're talking about if you've got 32 bits, again, for those of you who love math, that's 2 to the 32 power. And I didn't expect you to remember the number, but I did say please remember that this is roughly, give me an order of magnitude. People who are watching from home are kicking the screen right now that no one's answering this darn question. It is a lot. It's roughly 4 billion. So that means you can have roughly 4 billion computers on the internet using this IP addressing scheme. 256, incidentally, if IP addresses were only 8 bits long, you'd have 2 to the 8 or 256 possible IP addresses. Fortunately, we have way more. And it turns out that even though this might seem like plenty, well, the way that IP addresses are allocated throughout the world actually sometimes it's increasingly becoming tight, the address space. And some IP addresses go wasted because one person owns them but doesn't necessarily use them all and so forth. But there are ways of sharing, it turns out, IP addresses. And if you've ever wondered, if only tonight, how your home network uses one internet connection to share internet service to multiple computers, in effect, what you're getting when you sign up with cable modem providers or DSL modem providers is you are getting, yes, a physical connection to the internet, But more technically, you are getting from them one IP address. You are being assigned a number that is of this form that uniquely identifies you, your computer, on the internet. And by this form, I mean it's a number, dot number, dot number, dot number. And each of those numbers themselves can be from 0 to 255. So how do you see this? Well, let's make this a bit more real. Those of you with Windows, and again, I'm Windows biased in lectures only because this is what I bring to lectures. But if in Windows you go to your network connections and choose your appropriate network connection and click Properties, and this is the kind of details that ideally you never have to deal with these days. But if you scroll down, you'll notice something called TCP/IP. And it did flash on the screen a moment ago, but you actually heard that spoken by a big booming voice earlier tonight, right? He's TCP/IP, right? That was the teaser for tonight. Well, TCP/IP, I thank you for not laughing at me when I mimic the videos here tonight. So TCP/IP is the language that is spoken on the internet. Any computer that's connected to the internet speaks the language, or more technically, the protocol known as TCP/IP. So anything you do on the internet, for the most part, is carried across the backbone that we saw depicted earlier over using a protocol or a language called TCP/IP. How does this relate to your home connection? Well, notice when I double click on TCP/IP in that window, I get this box. And for 9.5 out of 10 of you, you never need to look at this or change this. Though a few years ago, this kind of tinkering was common. Notice that the top bubble check there says obtain IP address automatically. The bottom bubble says obtain DNS server address automatically. What that essentially means is that when I turn on my computer and am connected to my cable modem or DSL modem via wireless or wire, I am going to automatically ask my ISP for that IP address. It's not hard-coded into your computer. Years ago, it was not uncommon for a Comcast rep or the like to show up at your home with a printed piece of paper and say, here, type in this number as your IP address. And it came printed on a piece of paper. It doesn't work very well when you want to be able to change things and reconfigure things on Comcast's end. So things are almost always dynamic these days, at least for public networks and for utilities like Comcast and DSL providers and so forth. But what you get ultimately is an IP address. Well, what does this mean? Well, if you request a web page and you receive a response, well, what is in that response? Well, in our example that we always use, it's like the day's news, right? We said a week or so ago that web pages are written themselves in a language called HTML. Well, what does it mean then if web pages are written in HTML? And wait a minute, what language do web browsers and web servers speak? Did we say last week? What do you type when you type any URL? HTTP, Hypertext Transport Protocol, is the protocol that web browsers and web servers use to themselves transmit data. So I seem to be changing our story every week, right? Web pages are written in HTML. Wait a minute, web pages are transferred via HTTP. Wait a minute, anything on the internet is spoken in TCP/IP. Well, it turns out, and this is a very clever design fundamentally, most everything on the internet, so far as the implementation goes, is layered. So we began tonight talking about Ethernet. That's a physical layer, so to speak. Once you have a physical connection, you can do things with that connection. And with that connection, with that physical connection, you can put on top of that this language, this protocol called TCP/IP, that just gets the data from A to B. Well, what data do you want to send? Well, if it's a web page or a request thereof, you want to send an HTTP piece of data. So you have Ethernet, you have TCP/IP, and then you have HTTP on top of that. And what is in an HTTP response? Well, if it's for a web page, you get back HTML. So it's not that we keep changing our story. It's that we're looking at different layers of this puzzle that is the internet. And again, at the ground floor, you have the physical connection, something like Ethernet. On top of that, as of tonight, you have TCP/IP, which for right now, assume that that just gets data from A to B. Well, what is that data? If it's a web page, it's a chunk of bits that are stored in HTTP's format. Well, if that HTTP response contains a web page, inside of that is HTML. Well, let's try to make this more real. Suppose that I have made a request to, I need a volunteer from the back of the room. If someone could just call out their name in the back of the room. You don't have to come down to the front of the room. What's your name? Anyone? Abdul. So I wish to send data to Abdul. Well, I'm going to write this data, let's just say in English in some sort. Let's say it's an email, for instance. Here's my email. What I am going to do is hit the send button on my computer. What my computer essentially does when I hit send is it's going to figure out, oh, wait a minute, this is email. That's an internet service. I'm going to send that email out over the internet. Well, what language do I use to get anything out on the internet? I use TCP/IP. And one of the features of TCP/IP is in the interest of efficiency and in guaranteeing that all of your data gets from A to B, is it breaks it up into smaller chunks. And so I pre-tore tonight's paper, but imagine your computer essentially, without you, the user, even caring about these details, it breaks your message up into 4 smaller messages. Each of these messages go inside of what we'll call a TCP/IP packet. The packet will be sealed and it will be numbered. This is packet 1 of 4. Well, just like with the US Postal Service, if I'm going to send data to Abdul, I have to address this packet, this virtual envelope. So I'm going to write Abdul on the to field. And then just like you would in the real world, I'm going to say David in the return field, thereby addressing the envelope both to and from. You know, sort of a simple example to belabor, but what the computer's doing is precisely that. But my computer, suppose Abdul actually has a computer that I'm sending him this message via. Well, what's going to go here instead of quote unquote Abdul, based on what we've just learned? The IP address of Abdul's computer, or really to be precise, of Abdul's mail server, which might be Gmail or Hotmail or whatever. My computer figures out, based on the domain name in Abdul's email address, whose IP address needs to go here, Gmail's or Hotmail's or MSN's or someone else's. Meanwhile, we have 3 other parts to this message. So I'm going to go ahead and slip part 2 in the envelope. The computer is going to go ahead and seal it. It's going to become part 2 of 4. Abdul's name goes in the to field. My name goes in the from field. That's ready to go. I'm going to take part 3. It's going to go into the virtual envelope. Fortunately, computers do this much faster. This is going to be TCP/IP packet 3 of 4 from David to Abdul. And finally, packet 4 goes in its own virtual envelope. It gets sealed up. This is 4 of 4. And maybe an obvious question, why am I bothering to include the 1 of 4, 2 of 4, 3 of 4, 4 of 4? Just putting on one's engineering hat, so to speak. Right? You kind of have to know what order to reassemble these things. And to Abdul's computer, these are just going to look like bits. Well, together, they're all going to paint some picture of an email. But if you don't arrange them in the right way, it could end up being, say, gibberish. So the ordering is important. So that data is also included in these so-called packets. And now my computer, sometimes it feels like it takes this long, right, to send an email. So my computer is ready to send these packets, this email, off to Abdul. My computer, Windows, macOS, supports or speaks TCP/IP, so the computer out of the box just knows how to do these things these days. Well, where does this go? Well, my laptop is connected wirelessly to Harvard's network. So somehow or other, via 802.11g, these packets are going to be sent to these 2 antennas up here. They're going to travel then through the yellow wire in the wall in this building. That wire is connected to what piece of hardware somewhere in the building, most likely? A server, but we replaced server in our discussion earlier with a switch, which just is in a big wiring closet, probably somewhere in this hallway or in the basement. That switch, in turn, does in fact connect now to a device called a router. A router is a more intelligent computer that doesn't just spit data out ports based on what's physically connected to it, but a router rather looks at the to field and says, Abdul, Well, a router is going to have multiple connections coming into it and maybe going out of it. And just for simplicity, think of a router as having a connection going north, south, east, and west. A router is smart. A router understands TCP/IP. A switch only understands Ethernet. But a router understands TCP/IP and says, Abdul, inside of every router is a table of sorts, like an Excel spreadsheet or an access database. Essentially, rows and columns where the router can look up and say, all right, where is Abdul? And there's going to be a row, in a sense, in the router's table saying Abdul is to the north. And so what the router effectively is going to do is going to send these 4 packets as they arrive out its northbound port. Well, where are those packets going to end up? Odds are, Abdul's pretty far away from me right now. There's no direct connection between me and Abdul. In fact, for the sake of discussion, think of all of yourselves as routers. And I can reach Ray, but I can't reach Abdul. So it turns out that on the internet, just as our diagram a moment ago suggested, well, these circles that have all these points coming in and out of them, guess what those are? Physically, routers. So Ray, fortunately, is connected to another router via some leak, maybe one to the north, south, east, west. But each of these routers has a table that either automatically, that is dynamically, or because humans manually inputted this kind of information, each router knows the next best hop to send the packet. It might not be physically the closest, but it's the preferred next hop. Well, how does a router know? Well, obviously, packets aren't stamped with literal Abduls. That's why the beauty of using numbers as schemes is because routers can, for instance, look at the first few numbers in an IP address and say, oh, you know what? All IP addresses starting with 140 go that way. And all IP addresses starting with 141 go that way. And that's why the numbers are a useful scheme. So when I then hit send, my computer figures all that out, sends it to the access point, goes to the switch leads it via cable to the router. Maybe that router is connected to another one via fiber optic cable or something similar. Eventually, that router is connected via some other medium, maybe a transatlantic cable, maybe microwaves, maybe some physical landline connection. But in short, through one or more other routers is there hopefully a connection to Abdul from me. And just to hammer home this point, why don't we go ahead and I'll send them then in order to Ray, and to illustrate our point, don't necessarily send each packet to the same, let's send that one. Let's not necessarily send each packet the same way, because again, at any point in time, maybe a router's getting busy. There's a lot of internet traffic at some point in the country, and so a router decides, you know what, I'm going to route around this congestion into another router. Hence, all of those multiple paths between A and B. And hopefully this has soon arrived at Abdul. And Abdul, there is actually a real demo here. If you wouldn't mind opening up those envelopes that you've received and reassembling them and reading aloud, if you could, pretty loud, what the message is that I sent you. Oh, shh. Guess it doesn't work to whisper across the crowd. So you have all the envelopes that you've received. That goes without saying. And they were numbered. So read them, I think, if I did it right, 1, 2, 3, 4. I guess note to self, no self-adhering envelopes next year. And what do you got for us? The winner of the iPod Shuffle is, but it turns out, just as in the internet, as with TCP/IP, packets can be dropped, literally. And I don't know if a few of you saw me trying to be clever or witty, but I physically dropped this one on the floor, and that can, in fact, happen in reality. We're not talking about dropping something physical, but rather bits or packets. But TCP/IP is designed, or rather routers are designed, if they get too congested, let the sender retransmit. And again, it's an exaggeration, but a router will sometimes just drop your data. But that's why they're numbered, because built into TCP/IP in any computer that supports it is a realization that, wait a minute, if Abdul's computer thinking to itself, well, let's see, I got 1 of 4, 2 of 4, 3 of 4 wait a minute, where's 4 of 4? And he waits a second, 2 seconds, nothing's arrived. What Abdul's computer is designed to do, because it supports TCP/IP, as does Windows and Mac OS and Linux, he will request that I retransmit at least that packet that he hasn't received. And so what will next happen is my computer will say, oh, wait a minute, Abdul has informed me he didn't get this packet. I'll retransmit that same packet, and hopefully he will now get it this time. And just so I'll save you the routing of this, suppose I did send this final packet. Recall that the sentence that was read in great dramatic flair here was the winner of the iPod Shuffle for having submitted and scored higher than 75% on problem set 1 is a Mr. Timothy Conant. Timothy, are you here? Deafening silence. What a wonderful, dramatic surprise this is for Timothy, who will hear about this in about 48 hours, apparently. So as much as I'd like to just give it to Abdul, I'm afraid we're bound by the rules of this contest to give it to Timothy, who also was selected pseudo-randomly. But if we could, it will be preserved on camera. A round of applause for Timothy and for Abdul. All right. Thank you very much for partaking. So atop the slides here, we'll get that to Timothy, I guess. Atop the slides here, what you see is a more technical layout of what we've been talking about. It's not so important for tonight's purposes as to what the bits look like that are being sent across the wire via these routers. But just to put things into perspective, even though we keep calling it TCP/IP, TCP/IP is actually 2 different protocols that are just so commonly used together that people usually refer to them as a pair. But this, it turns out, is what a TCP datagram or TCP segment looks like. Well, what does that mean? Well, any piece of information that's sent via TCP is laid out in this fashion. And you don't have to really absorb all of this, but all this means is that you have the first bit, second bit, third bit, fourth bit, fifth bit, essentially laid out from left to right, top to bottom. Embedded in this TCP packet, then, is some interesting stuff which should make intuitive sense. Notice this: a sequence number, an acknowledgement number. Well, what was I doing in the top right of the envelope? I was saying 1 of 4, 2 of 4. That was the sequence number. So embedded in each of those envelopes or TCP packets is precisely that number, using, in this case, how many bits are used to represent a sequence number? If this is 0, we got 10 bits reading so each of these dashes represents a bit. So how many bits? 31, or we're counting from 0, 32 total bits are used for the sequence numbers. Now, this might seem silly. How often am I going to send Abdul an email that requires 4 billion packets to be sent? Well, your computer's doing a lot of other things at once. So these sequence numbers aren't just for one email, but for all of the internet traffic that your computer is sending. So it's useful to have so many different options. Source port and destination port. These, I think, came up briefly last week, though I tend to confuse semesters, so help me out. What port does HTTP use? Am I remembering? Am I in 2006? 80. 80. 80 sound familiar? Yes? No? OK, so let's talk about ports. So I thought we did this last week, but you know that a server, a computer, can do multiple things at once. It can provide multiple internet servers. One computer can be an email server. It can be a web server. It can be an SSH server, which is a technology you'll use in section if you haven't already. In short, a computer can do multiple things. But if a computer only has one IP address, well, that sort of begs the question, how does your computer distinguish whether some bits that are arriving are that reply from Abdul or that web page from CNN? Well, associated with every internet service, and by that I mean HTTP, that is web, email, Google Talk, AOL Instant Messenger, all the popular programs you can think of, Skype last week, is a number. A relatively small number like 22 or 80 or 1,000, but relatively small, that uniquely identifies the type of service that that packet includes. So if I wanted to be really particular on each of those envelopes I sent to Abdul, I would have written the number 25, which is the port, the number that uniquely identifies email on the internet, aka SMTP, the sending of email. Well, inside of this TCP packet then, are those numbers, so that when Abdul receives that envelope, his computer can say, oh, you know what? Not only do I know this is for me and from David, it's an email, which means I should route it, in effect, to Outlook or to Eudora, instead of to, say, Internet Explorer or Firefox or a browser. So those are ports in a nutshell. Meanwhile, it's in IP. Do I have this picture here? Yes. It's in IP, just to give you a glimpse of this, that we actually store the so-called source address and destination address. But again, we would defer to like a networking course to tease apart more of these features. But we can see them in action. What I have here is a window. It's a little small, but hopefully you'll see it when it fills the screen. What I'm going to run in a second is a program called traceroute. So I am connected right now to one of Harvard's computers in the electrical engineering and computer science building. So it's, a few buildings away. That's fine. Think of it as being on my laptop. What I'm going to do is ask the computer, show me the route between my computer and CNN.com. So I'm going to run traceroute, as the program's called, www.cnn.com. And here are the results. So there's a lot going on, some of it pretty fast. We're up to 16. Now notice, some of these won't work for us for various technical reasons, but notice that the very first line just reminds us, traceroute to CNN.com. What's this in parentheses then? Of the IP address of CNN.com's computer. Good. Notice that this first line here starts with 140.247.60.1. A useful hint, but this is not always true, but it's often true in the home. With your home routers, a router's IP address usually ends in .1 by convention, but it's not a requirement. It's one of these conventions, useful heuristic to recognize things. So what does 1 represent, do you think? What does line 1 represent? Landline, right idea, not quite right though. Keep looking ahead. So we're talking in terms of hops again. What does each of these rows represent? Take a guess. Server of some sort. What type of server? Backbone of sorts, but what does each of these hops, again, I'm trying to use the same nomenclature, hops represent? A switch is just a local thing for your local network. A node, yeah? Looking for a word, starts with R. Router. Right, so routers. So this has been the buzzword most of tonight. A router, again, is just a device that gets data in, figures out, oh, this IP address goes that way. Let me send it along to the next router. Well, who's the next router? Well, for my computer, the first router is that guy depicted in line 1. Who is that router in turn connected to via some kind of physical connection or wireless connection? Well, the router in line 2. What's its name? Well, the host name of router number 2, to borrow last week's lingo, is this rather cryptic core-1-GWs-V1415, but thank God, something familiar, .fas.harvard.edu. So this is one of the Faculty of Arts and Sciences routers. GW is a common nickname for gateway, aka router. A gateway is a router and vice versa. What's in line 3? And I'm going to stop it before it scrolls too far for us. What's line 3? Well, that looks like yet another router. Notice one buzzword in there, useful to at least see this stuff in practice. WAN, so some kind of wide area network. But these host names are completely the prerogative of Harvard sysadmins. They mean nothing in and of themselves. They've just been chosen by some tech guys. 4 looks like it doesn't have a host name or domain name per se. And that's OK. Not every computer on the internet needs a name that's human memorable. Because who cares what the name of a router is, frankly, often. You just care about your own computer or the destination. But moving on, take a look and make an inference here. Where is my data going from the moment it leaves my computer on its way to CNN? What happens in step 5? Where are we? So we're in Boston on Quest's backbone. Quest being a big ISP of sorts, a big backbone provider locally. So it looks like our data hops around Quest's network for a little bit. But turns out that between lines 6 and 7, where does our data go geographically? Sorry?
Like it seems like you're going from a city to like a big core wire to a larger big core wire.
Good.
To wherever the wire hub is, and then back out 1 or 2 levels to where the address is that you're reading from.
So good. So in Spirit, and what's often happening is your data is leaving your computer, going to faster and bigger computers and connections, and then eventually on the tail end, the process effectively will tend to reverse, at least if you're visiting a somewhat small site. But again, the question on the table here, what looks like, tell me something interesting about where my data is going between points hop 6 and 7. Use your airport codes. I know this one. I grew up in the tri-state area. Hint, hint. Yeah, come on. 33% chance of getting this right. Newark. EWR is the airport code for Newark. This, again, is convention. Not all routers are named with airport codes, but sysadmins tend to use it because it's useful, a useful convention to obey. So literally, between points 6 and 7, assuming they're not fudging the host names, there is some kind of physical connection between Boston and a router in Newark, New Jersey. How much time does it take for my data to go from my computer to Newark? Well, that's what all the other numbers on these rows are indicating. In parentheses is each router's IP address. But to the right of each router's IP address, say right here, 6.983 ms and 6.700 ms. What is that, do you think? Sorry? Milliseconds, and that denotes the number of milliseconds it took for my packets to literally go from my laptop to Newark, New Jersey. Right? It takes 5 to 7 hours to drive there. It takes 6 point some odd milliseconds for those virtual envelopes that I sent to Abdul to get to Abdul in Jersey if he were there. So when you start talking about speed of light and electricity and fiber optic cables, in theory, traveling up to the speed of light maximally, I mean, 6.7 milliseconds to get from here to Jersey, that's pretty darn fast. It certainly blows away any sort of physical transport mechanism we've yet invented. Yeah? Good question. Why are there 3 of these numbers? Well, this program in particular, just to give you a sense of averages, tries to send the data 3 times. So that you can look at it and say, all right, 666, that's a pretty good estimate. Because sometimes, again, you'll get congestion. And if you were just to see something like 15 milliseconds, you might infer that, oh, there's a bottleneck there, but it might have been very temporal. And it might disappear the next time. And what this program's doing, it's not sending emails, it's not sending web pages, it's just sending, let's say, empty envelopes. But in such a way that we get a response back that measures the amount of time it took to get there. Another question. So why does it go faster from Boston to Newark? What you're actually seeing, these times are the times from my computer to that router. These aren't the times between routers. So in what you would hope you'd see, and what we are generally seeing, is that as you look from top to bottom, these numbers are in fact getting bigger and bigger. And that's consistent with the distance getting slightly farther and farther away. So read them from start all the way to the router. Let's take a look. I don't know what DCX is. It might be somewhere in DC, but I'm not familiar with it if it's an airport code. The others are a little more cryptic to me. And sometimes you'll get these stars, which just means the routers are not set up to respond to our kinds of requests. But let's try another one. Let's say something like, I think we said cnn.co.uk is the UK version of CNN's website. Well, let's give this a try. OK, there we go. Notice that there's similarities in the path, which you might expect, because the data is being routed through some common point. Notice, and you can see it here, just for some reason, notice line 11. The numbers are all over the place, but it looks like it was a temporary bit of congestion or something. Because notice it took us, over, where'd the value go? Here we go. 185 milliseconds to get to hop 11, but clearly we can get past that more recently. It looks like the routers along this path just aren't being very cooperative. Let's try something in the other direction. So .co.jp for country code of Japan. Let's see what we get this time. OK, we got the first few. All right, so now we can start using our airport code tricks again. So we're going from Boston to where? New York, JFK, airport city code. SVL and PAX. Any guesses? Sorry? It's in this country, and you can infer that from the times. Let me ask you this, though. Tell me between which routers is there a really expensive, really thick, really long trans-Pacific cable or transatlantic? Yeah, take a look at that, and you can read something interesting into these numbers. To hop 11, it takes us 75 milliseconds. To hop 12 from here, it takes 200 milliseconds. That suggests a really big something. In the middle, odds are it is, in fact, the ocean. And if I were better at inferring from these host names where they are, I could tell you if it's going to the east or to the west. Since it's going PAX, we can look this up later. But there, that one made it all of the way. So to go from here to Japan, which in a plane would take many hours, with Google Earth even would take a few seconds, with the internet itself, 200 milliseconds. You can get there and back in under half a second, literally. It's kind of a mind-blowing thing. So how does this all fit together? Well, let's take us as promised.
Time in history, people and machinery are working together, realizing a dream. A uniting force that knows no geographical boundaries, without regard to race, creed, or color. A new era where communication truly brings people together. This is the dawn of the net. Want to know how it works? Click here to begin your journey into the net. Now exactly what happened when you clicked on that link? You started a flow of information. This information travels down into your own personal mailroom, where Mr. IP packages it, labels it, and sends it on its way. Each packet is limited in its size. The mailroom must decide how to divide the information and how to package it. Now the package needs a label containing important information, such as sender's address, receiver's address, and the type of packet it is. Because this particular packet is going out onto the internet, it also gives an address for the proxy server, which has a special function, as we'll see later. The packet is now launched onto your local area network, or LAN. This network is used to connect all the local computers, routers, printers, etc. for information exchange within the physical walls of the building. The LAN is a pretty uncontrolled place, and unfortunately, accidents can happen. Packed with all types of information. These are IP packets, Novell packets, Apple Talk packets. They're going against traffic, as usual. The local router reads the address and, if necessary, lifts the packet onto another network. Ah, the router. A symbol of control in a seemingly disorganized world.
Oh, sorry about that. This one here, this one here. Oh, this one's here, this one was here. I don't like this one. Let's go this one, this one's here. Oh, this left one, this one, this one here. Let's go down here. Let's put that one here. Let's put that one. Let's put that one here.
There he is. Systematic, uncaring, methodical, conservative, and sometimes not quite up to speed.
Sorry.
But at least he is exact. For the most part.
Oh, another one was there.
the packets leave the router, they make their way into the corporate intranet and head for the router switch. A bit more efficient than the router switch plays fast and loose with IP packets, deftly routing them along their way. A digital pinball wizard, if you will. As packets arrive at their destination, they're picked up by the network interface, ready to be sent to the next level. In this case, the proxy. The proxy is used by many companies as sort of a middleman in order to lessen the load on their internet connection, and for security reasons as well. As you can see, the packets are all of various sizes, depending upon their content. The proxy opens the packet and looks for the web address, or URL. Depending upon whether the address is acceptable, the packet is sent on to the internet. There are, however, some addresses which do not meet with the approval of the proxy, that is to say corporate or management guidelines. These are summarily dealt with. We'll have none of that. For those who make it, it's on the road again. Next up, the firewall. The corporate firewall serves two purposes. It prevents some rather nasty things from the internet from coming into the intranet, and it can also prevent sensitive corporate information from being sent out onto the internet. Once through the firewall, a router picks up the packet and places it onto a much narrower road, or bandwidth, as we say. Obviously, the road is not broad enough to take them all. Now you might wonder what happens to all those packets which don't make it along the way. Well, when Mr. IP doesn't receive an acknowledgement that a packet has been received in due time, he simply sends a replacement packet. We're now ready to enter the world of the internet. A spider web of interconnected networks which span our entire globe. Here, routers and switches establish links between networks. Now, the net is an entirely different environment than you'll find within the protected walls of your land. Out here, it's the Wild West. Plenty of space, plenty of opportunities, plenty of things to explore and places to go. Thanks to very little control and regulation, new ideas find fertile soil to push the envelope of their possibilities. But because of this freedom, certain dangers also lurk. You'll never know when you'll meet the dreaded ping of death. A special version of a normal request ping, which some idiot thought up to mess up unsuspecting hosts. The paths our packets take may be via satellite, telephone lines, wireless, or even transoceanic cable. They don't always take the fastest or shortest routes possible, but they will get there. Eventually. Maybe that's why it's sometimes called the World Wide Wait. But when everything is working smoothly, you can circumvent the globe 5 times over at the drop of a hat, literally, and all for the cost of a local call or less. Near the end of our destination, we'll find another firewall. Depending upon your perspective as a data packet, the firewall can be a bastion of security or a dreaded adversary. It all depends on which side you're on and what your intentions are. The firewall is designed to let in only those packets that meet its criteria. This firewall is operating on ports 80 and 25. All attempts to enter through other ports are closed for business. Port 25 is used for mail packets, while port 80 is the entrance for packets from the internet to the web server. Inside the firewall, packets are screened more thoroughly. Some packets make it easily through customs, while others look just a bit dubious. Now, the firewall officer is not easily fooled, such as when this ping of death packet tries to disguise itself as a normal ping packet.
It's okay, go on, it's okay. No problem. Have a nice day. Be out of here. Bye.
And on that note, we'll leave the ending as a surprise for next time. We'll see you next week when we will dive into new material altogether.